So, hello guys. Welcome to the computing workshop. I'm the mad computer scientist, and today um, I'm going to delve into a topic that was brought up as a question originally about spell checking and actually how people did spell checking back in the old word processors, and also how it's still being done, the spell checking in general, which is a more interesting subject than you may think, because um, it has a long history of complexity, and actually a lot of research over the years has been done on doing spell checking and word matching, and there's an entire field of computer science which is basically dedicated to this type of research, with basic basically string matching algorithms of various types. Now, ever so to delve into this subject, we will look at one of the most important pieces of one of the most important articles in Dr. Dobbs' journal, and we will also implement the algorithm described in this article, which was a very seminal piece in the late 1980s on this subject. Um, but starting at the beginning, ever since the world was introduced to software word processing with the release of Electric Pencil in 1976, WordStar following in 1978 for the CP/M operating system. One of the most requested and used and most discussed functions of such software has been the ability to correct mistakes and to scan text for composition and for formatting. This type of automation in these early word processors was pretty much the selling point. Now, WordStar, for instance, has block editing capabilities that has made it famous. That allows for easy recompositioning of text. So, and this is a WordStar screen that you can see, early version of WordStar. So, however, in the early days of software-assisted text entry and also formatting, so there wasn't enough power in the computers at hand to do more advanced functionality that you see and take for granted today. And one of the functions that people started to demand early on, but that proved very hard to get working, was to automate the work of a spell checker, which by then, in the earliest days, was an actual human that would read through memos and such and identify spelling errors and suggesting corrections, most notably using a dictionary. In 1980, the topic of spell checking documents entered into a computer memory, was one of the key discussion points of the IAA conference. So this is scientifically being discussed in the early 80s, how to get an efficient algorithm for spell checking. And today one may take this functionality for granted, and even your email client will do this on the fly for you while editing an email text. But back then, this was a very hot topic of academic study. So if you, by it's a very trivial function today, which is very interesting. People take this for granted, and it may seem like a trivial function these days, but programmatically it proves quite a challenge, especially in a constrained environment such as in the early microcomputers. So if you think about spell checking a word, you would realize the complexity. So first you must isolate the word, and then you must have some sort of list of valid words that you can check the word against. And in the naive implementation, this would mean having a large dictionary and then comparing the word letter by letter to each entry. So needless to say, this is very time consuming. So some clever use of hashing and various tree structures has been discussed over the years, and algorithms have started to appear early on that could spell check words. These algorithms were then implemented in various forms by the biggest names in word processing at the time, with a varying degree of success. Often they early on required the dictionary to be kept on a separate disk, and it was still a slow process. I mean, it it took a while to spell check a full document, but it became a very appreciated function. But now, to add further complexity, imagine that you want to not only check if a word exists in the list of valid words in that language, but also do what modern spell checkers do, which is suggest possible valid words. So, like not synonyms, you want to suggest like possible correct spellings of what it thinks that you were wanting to spell. So the complexity then increases again. So now you not only have to figure out how to quickly process a list and do basic string matching, you also need an algorithm to score possible words that could have been what you meant to type in order to suggest the most likely candidate. This advanced form of matching was not a thing in word processing until much later. However, it then became an integral selling point of the packages that could offer it. Uh, there is an important piece of computer history hidden here. We will look at two examples of this in WordStar 4 and so let's look at some spelling examples. So going into the trusted old 386 DOS environment, this turned out to be a Swedish version of MS-DOS, but it doesn't matter. I started WordStar 7, which is the early 90s version. This is the last formal version, 7.0. And I still love this editor, by the way. WordStar is like the best word processor ever. Still use this basically every day. But let's look at once you learn how to work in WordStar. By the way, you will never want to, according to me, you would never want to work in another word processor ever again, because it's so fast and the block editing features are just so good. So this is WordStar 7 on a 386 20 megahertz PC, and we can use this to show an example of one of the earlier spell checkers. Let's type, I don't know, let's type, what the hell's up with this? And switch the keyboard. Let's type this, and instead of banana, and see if it can figure it out. So then we have to move cursor all the way back, and we press Control QN, and yeah. So you see, Control Q is go to start of line, and N is spell check for the word. So Control QN is the control character in WordStar. You go back to first, so check from the first character and check one word ahead. And here you can see that it found a suggestion after some computation time, which is banana. So we press 1 and we replace the word. Smooth as that. So we can exit WordStar instead. Don't want to add that. So looking at another example, let's do this. Let's see if there is a oh my. Okay, so there's a Windows 3.0 on this machine, and now whoa. Okay, so it's a Swedish Windows 3.0 on this machine. That's interesting. So, oh my, when I forgot how Windows 3.1 actually changed this to much better, looking much better. This actually, so this is Windows 3.0, but there should be there's a Swedish Microsoft Word 2.0 here. So let's use that to show the Microsoft style of spell checking. Yeah, it's a lot of Swedish there. This is actually my old 386 hard drive. I actually use this when working. I actually used this installed professionally uh, back in the day. Let's type a typical Swedish word which you won't know, which will be like this, Fisk, which is fish. But let's misspell it by adding an A instead. So, okay. So now, using this, we can have under tools, we do spelling. Yeah, and it adds a bunch of suggestions with, now you can see where they use a similar, and this is the dictionary it's using. You can have your custom dictionaries. Just ignore for a moment that this is in Swedish, so sorry about that, but yeah. But now it figured out there was some words that could be matches, and this is because now it's actually using something similar to the algorithm that we were discussing. It's using, you see that it arranges the words in order of score, like the most probable match. And if I double click that, it probably, yeah, so it'll probably replace it. Yeah. So it uses this type of scoring algorithm, maybe not exactly the one in the article, but very similar. So this is okay. Yeah, let's quit that. See if the capture card is still getting the resolution properly. Yeah, so we can see that these are some early examples of this. Now, if I can just end the capture screen. Oh, yeah, that's the mouse pointer from the recording computer. Let's see what's going on. Okay, so maybe, yeah. Okay, so I'll figure out a way to also end this this video capture from the VGA. And we'll continue. There is an interesting piece of important computer history hidden here. So Dr. Dobbs' journal, which is one of the oldest publications on computing in general and a very influential outlet that came from the early PCC movement, went from being a very amateurish like Xerox copied magazine format into a professional printed magazine and journal. And in the July 1988 issuing, it had an article on string pattern matching that was titled Pattern Matching, the Gestalt Approach, that went on to become the basis of many implementations of the word suggestion function in word processors and editors. So instead of complex rule-based methods like the so-called RETI algorithm, it favors recursive function calls on a smaller and smaller character set, recursively computing the match score between the input and the reference. Here's a picture, a scan of that article, or part of this article, together with example code. So when combining this with fast list parsing and various hashing routines, you can create a weighted list of the possible near matches, just like you would see in modern spell checking. So this article was entered by a fellow named John Ratcliffe and David Metzner, both at the Cardiovascular Research Institute at St. Louis University. And it's credited to Ratcliffe and to John Obershelp. So the article describes the recursive approach, and it includes source code and the runtime examples for what was to be known as the Gestalt pattern matching algorithm. And being as influential as it was, the article was read by many computer hobbyists, and variants of this algorithm started appearing in other publications. And versions of this algorithm still form the basis of many established text editing products. And it's a very important piece of software engineering. And at its heart, it's a rather simple conceptual and mathematical idea. So let's draw an example of it. Okay, so let's look at an example of say of this formula. Um, let's say we have the words. Let me just switch the screen. Let's say we have the words banana and this extremely weird spelling. Maybe someone had a stroke or something while typing, but we want to use the algorithm and its associated mathematical formula to figure out what is the score, the matching score of these words. And then we will, this is just, the banana would be the target word that we pull from the word list, and this would be the actual, what you typed. And then we want to see how similar they are so we can get a metric on that. And then as we go through our word list, we can check if we can find a greater match. If so, that is more likely to be the matching word. But let's see the base formula that we can distill from the algorithm is given two strings, which is we call S1 and S2. The formula, let's have a pen. The formula is like this. So it's 2 times k of m over the length of string 1 plus the length of string 2. So by and this is a typical representation of this algorithm in a mathematical form. What does this mean then? If we want to compute the scores here, so we can do that. Let's see. Let's plug them in. So for each word, target word, we would run our input word against this function to determine the score, the match score. So in this case, we will start from the left and we will compare. So B and P doesn't match, so that's no match. Then we will see A and A. We will see AN here, which matches with this AN here. So here we have a match. So we will have a match of two characters. Okay, so we write that down. So we have two matching characters in this group. Now we check that what is to the left of this group that we matched, we have already checked. So we don't need to check that. Okay. What is on the right of this group, however, we haven't checked. So we need to check that. So we check on the right side of this, and then we can see that we have A and U. So this is not the start of a matching group. Okay, so we check. We have already checked to the left, right? So there you go. So we check to the right. See? So by checking to the right, we can now see that we have NA and NA as a matching group, also with two matching characters. So what we end up with is 2 times 2 plus 2. Okay, because now our recursive, where we split and check the next one, this one will end. So now we arrive at the last character, so we will have to end our recursion. So now we have 2 times 2 plus 2, which is 4 there, and 2 times 4. Let's do this step by step. So 2 times 4 is 8, right? So we have 8 for the top row over the length of string 1, which is 5. Okay, so it's actually it's 6. Sorry. So banana is 6 characters. So we have 6, and the other one is also 6. So plus 6. So 8 over 6 plus 6, which is 12. So we have 8 over 12. This is our matching score. Now, let us bring up the trusted old Windows calculator and say 8 over 12, and we have 0.66 something. So we have 0.66 is our matching score, or the probability of this being the word is 66%. Okay, so by now you can see how this algorithm operates, and then we run the same check on each and every on each of the words, so that we get we get the correct scores, and then we see which score is the greatest one, and the greatest one is the one we choose as the possible best match. Yeah. A further thing that now that I cleared the drawing board, the further thing that we uh, um, have to work out to look at the code later is the idea of recursion. I mean, some of you will know what this is, some of you won't. It's basically uh, self-calling. So let's say we have a function which is called do stuff, this, and it takes some sort of variable here. It takes an input of some type. Now, if the input is, let's say the input is an array, which is a sequence of values. Let's say that the input is a string um, of characters like hello. So we send this to the programmatic function, and then we say we have a divide and conquer algorithm based on something, I don't know, based on looking at parts of the, let's say the string is a bit longer. It's like hello world or something. A typical divide and conquer algorithm would do some sort of computation based on smaller and smaller steps, and then call itself. And as you call further down in the like if you have the original function call here, then you call the same function again, and then you call it again, and then you call it again with smaller and smaller subsets. Eventually you reach some sort of end condition where the calling ends, and as you return from the function call, you're going to sequentially return through this call chain and end up with the result of all of these calls. Like, let's say we had the first call to the function, look at these two values, maybe do some calculation, and then we do a recursive call on these, and then the next, now you would have two function calls. We call do stuff again. It calls itself with like I don't know, let's say the result of these two. So now the input is like this, and the input is like this. And then the next call is take the two middle ones, which let's say is this, and check those, I don't know, and then call left and right. And here it could be an end, because we could have a check if let's say input is less than 2, then we end and we return 0. So that would end the function. Same thing here, and so on. And here the return is this computation, and then this computation. It's the same thing here. You would check this, and then you would split off down here. So this is each consecutive calls, self calls from within the do stuff function to itself. So this will build the call stack. So that's 101 on recursive function calls. This is of course very useful in divide and conquer algorithms, where you want to look at a smaller piece and then split off and do a typical example of this is the famous quicksort algorithm. And as the As the finale of this rather long-drawn expose on a rather narrow subject, I will attempt to hack together my own implementation of this algorithm based on the original article and uh, my previous understanding of the obershelp algorithm. So I have implemented a variant of this before professionally, but that was many years ago, and I basically remember nothing of it. So I'm going to simply dive in after reading through the article again, and I will ponder the problem for a while, and then I will try to hack up something that can give suggestions for partial matches of an entered word. So maybe it works, maybe I fail. So we'll see. And in editing, I will probably speed this part up so you don't have to watch me typing and correcting any mistakes in a real-time snail pace. Then we'll run it and we will see what happens. And I will use free Pascal for this. Why? Well, it's a modern, still updated open source offspring of Turbo Pascal that should basically tell you why. But it's because everyone should use free Pascal at any chance they get. And the fact that Pascal is a very readable programming language, it's very simple to hack something up. In a real world setting, we would likely not write in Pascal, but something a lot more hipster and currently trending. And we would also not write as ugly, hacked up, butchered code as I am likely about to do now. So we'll give it a try. Yeah. Okay, so that was grossly boring. So I cut it out. There was a lot of code. So let's, as you can see, a lot of code that I wrote in the end. Also, some of the stuff probably this is very quickly hacked together. So let's see. Um, let's just go over some of the concepts in the code instead of watching me entering all the code because that's enormously boring. So the idea is to get a word list from a file. In my case, I call it words.dat, and in this file, from this file, I pull the valid words. Okay, so I just read in, and in this case, it's hard-coded to be 10 words, which of course you would not use in a real-life scenario, but we read in 10 words from this list, and we add it to the lookup list in memory where we have the valid words, okay? And then we get the input word, which is what you actually want to spell check, and then we figure out which the best matching word is. And we do this by calling the function best match with the input word and the lookup, the lookup being an array of we pass the word list. This is also something you would probably not do in a real life scenario. You would probably point to a word list already in in memory or in some external storage. If we go to best match, the point of this function is to figure out which of the matches found is the best one, the highest matching score. Remember, the algorithm gives a scoring. So if we have multiple matches, it will figure out which of them is the most probable, what you were trying to spell. So here we get all the scores, and then we do the algorithm as we looked at before. So this is basically the formula that we saw before. And then if this new matching score for this, we go through all the words, and then if this new matching score is higher than the previous matching score, then we set this to the matched word. Okay, so we check each and every word on the list. This, of course, is also something that you would have to combine with some other algorithm in real life, like hashing or something like that, to just look at a portion of the list, because now we are iterating the full list, checking each and every word to see if we can get a better match. And this would take enormous amounts of time with large word lists. So normally you would combine this with some sort of tree structure or some sort of hashing to just look at a portion of the list, or a subnode, or a set of subnodes in the list. So you could probably enhance this with at least with some sort of hashing algorithm to get it to the right region of the list to limit the iteration. Now this uses the getScore method, and getScore is the actual recursion. Which is a very long method, which we will look at very briefly. So I use a lot of variables here. So we take the two input strings to match. Remember, this is recursive, so we will shrink this and take the left and right portions separately, and recursively we will call this function again with the smaller subset, the smaller substrings. So we have a lot of variables here to keep track of stuff. And then we initialize all the variables. This is old school, but this you don't have to, normally you don't have to do this in many of the more modern programming languages, especially not the ones that are like JavaScript and so on, because they have implicit they are more freely typed. In this case, we initialize all of the variables to make sure that they have values. Now the split index end is set to 9999, meaning that we want actually infinite to begin with. But we set it as a higher integer, longer than any probable string. And then we check that if we are at this is the end condition of the recursion, and this is a head recursion. Remember that we check first, before we do anything else, we check if we are at the end of recursion. So we check that if our we have a smaller left or right hand string than 2, meaning that we don't have anything left to check on either side, on this side, then we return 0 from this recursive run. So the return is 0. This is the Pascal equivalent of return, by the way, setting the value of the name of the function. So if you're familiar with C, this would be return 0. In the Pascal case, it's assigned to the label of the function. Or if it's not, then we can begin a new computation. So then we do some length checks, of course, and then we step through and compare the characters. And this is just like we saw in the algorithm. So we do, first of all, we set some more lengths. The actual checking is here. So if we are matching, you find a matching character, then if we are not already in a matching, remember, we want to find the score, the longest consecutive matching substring. So if we're not already in a matching substring, we start a new matching substring and we start matching the characters. So the subsequent characters belong to the same matching group. And then that's basically what this is. And then we update our split index because the split index start and end is where we want to check on the left and right hand side of this largest matched group. So we want to take everything that's to the left of that and everything that's to the right of that and recursively call this function. Otherwise, we set the matching to false. Once we find it doesn't match anymore, then we end this matching group. Now, by going through that, we can then do we set the new we set up the new call, okay, and then we do some length checks on the split indexers just to avoid stepping outside of the string boundaries. And then we do the recursive call. So we call getScore again from within itself, and we do. You see here we set the return, the eventual return after all of the recursions. Remember that without the ending condition returning 0 at the final condition, we would just fill up the stack and we will crash the program. So we, like in all recursion, we need an ending condition. Which we looked at the top. So we send the score of this one plus the recursive scores of the left-hand side, the right-hand side passed in, like the start and end of the left portion and the start and end of the right portion. And then we start matching again. So eventually we will add up all of these recursively. And finally, we will get everything unrolled from the stack calls all the way back up. And we will go out from getScore with the matching score. So we call getScore for each word. And we do the recursion, then we do the computation, as we saw in the algorithm description, and then we update the matching score, and finally we find the best match, which is the one with the highest matching score. So this is basically it. If you want the full code, you can just ask me for it and I can give it to you. It's very much unclean, very hacked together, probably filled with errors and whatnot, because I just wrote it from the top of my head. I can see already that there are some of these variables that I set that are not even used, but never mind. So I just did this from the top of my head and by looking at the article. But first of all, let's see that it actually works. So we can compile the code, make the code, or make it into an object file, and then we build our executable program, and then we can go to the command shell. Should we call the exe file, should be called this, right? And I have some words in my word list. Okay, so now it wants me to enter a word. Let's say we misspell apple. Should have 2 P's, right? And apple is in the word list. So we do this. It figured out that I probably wanted to spell apple. Let's try another one. Let's try, I don't know. I don't even remember what I put in the word list right now. I think I put where. So that's a common misspelling, like doing this. Especially if you're a non-English speaker like me, you commonly do this. Yeah, okay. So it figured out that I wanted to type where. Okay, that was the best match. I also put where with some A or something in the word list. So in this case, the recursive scoring is working because it figured out that since I got the E correct at the end, but not the H, it determined that it's probably this word that I wanted to spell. This means that it's actually working as intended. That's good. So that's the basic gist of it, is that you keep doing the recursive calls, and then you unroll the stack so you get the final score. And each recursion you pass in the left and right indices to check the substring to the left of the matching portion and the substring to the right of the matching portion until you get the final score. And then by looking at the final scores for all the words you were looking up, you can determine the best match, being simply the highest score. So that's the main point of all this. So apparently, the I managed to implement the algorithm sort of as according to the article. So this shows that this is in fact a usable algorithm. You have to uh, add certain things to it, like, for instance, the hashing, so you don't have to iterate a large word list, of course. But that's additional algorithms that you add on top of this. But as you can see, it quickly becomes, if you add those other algorithms to this, and then some other more complicated things like having separate word lists and stuff like that, this this seemingly trivial feature actually gets quite complicated. And there's a lot more complicated algorithms used today in things like the Google stuff for like Google Docs and stuff like that. Doesn't use this. They use large lookup trees, I think, and things like that. Something known as a trie algorithm. So it can become very, very complex for what seemingly for a human is a rather simple task, but for a computer is actually quite complicated. So